Hey guys, so let's get back to this. I assume you can hear me okay, right? So today, like, let me quickly recap what was happening last time. So we looked at the boot system, which which was created by Zafang and myself at some point, and it allows us to say, look, we take maybe switch to drawing something because I like drawing. Essentially, what we can do is that we said, look, if we have a collection of Rust files, and specifically have just like the file which contains the main function, but like we also can use anything else like additional code which we develop, and also this all through the Rust ecosystem depends on external crates, and we use crates like Spin. We will be using x86 crate. We'll use like lazy static, stuff like that, right? Essentially, our build system allows us to take all of it and essentially, okay, hold on, all of it plus a couple of assembly files, and the two ones we care about is a boot asm, and the second one is the multi-boot header.
You can turn it up.
Yep, excellent. Shall I just mute you?
Oh, sorry.
Yeah, no worries. Essentially, so we know how to take Rust files and ASM files, and we use the tiny build script. Let's build a RAS, and we use a make file to invoke cargo, which will internally invoke build the RAS. And we also used our wonderful linker script. And I forget the name. How do we call it? Just quickly switch. Is that what was I calling my build script? This hopefully linker something. One more didn't work. Alt top doesn't always work, but otherwise makes sense. That's not it. What do I want to see? Like, okay, linker script essentially. The linker script is important because it says, look, I want a specific layout and I want to put the multi-boot header here. Like essentially, linker script is important for two things. So it controls the position of the multi-boot header, and that's one. And the second one, who can tell me the second one? Just to make it more interactive. Does anyone remember what else we did with this linker script? Anyone? Anyone was following? No one remembers. Come on. At least, do you guys remember the linker script? Do you guys remember the multi-boot header?
I remember. I just don't remember what goes after. I thought it was like dot start or something.
There it was what?
I thought it was dot start, but I think I'm just making that up.
Yeah. Wait. The second most important thing is that to tell the linker what is the entry point, right? Because it doesn't like normally you say, look, main is the entry point, but it's linked against the runtime. So the runtime becomes the entry point, eventually calls main, right? But in our case, there is no runtime. So we say, look, these two things are important. So the start label and the start label, do you guys remember where it lives? start is part of this assembly file, boot.asm, right? We will take a look. We'll look more at boot.asm today. So essentially, entry point, right? And so we have that's our build infrastructure. So we have a make file. Let me just use a different color. Internally, it uses cargo. Cargo uses build.rs. Build.rs says, okay, I have dependencies on a couple of assembly files. And there is also, like, we specify that the linker string, like in the cargo toml, we specify that we should use I'm sorry, in this, not in the cargo toml, in this, in the target itself, we say that the linker should use the linker script, linker RLD, it's called, right? And what it gives us is that, like, if you type make, it kicks in, make file goes first, cargo goes second, build script, and then eventually everything is compiled. Compiler runs Rust, NASM assembler runs NASM, processes assembly files, generate object files, and finally the linker runs. Okay, we can say, like, this is 4. Finally, the linker. This is 5, let's say, which uses the linker script, right? And at this point, we get in a build folder, we get our hello OS, right? So let's take a look. So we do make clean. Do you see my screen? You probably do. Let's move this one somewhere. Then if we do something like make, everything runs. So since those are the crates we depend on, so like x86, spin, volatile, lazy static, another version of spin, not sure why, maybe wrong. But essentially what it does, it generates build hello OS, it's a file. It's Jesus Christ, what is this LS? It's roughly 2 megabytes in size. And okay, but this is our kernel. And at this point, I wanted to show you a couple of things. So normally we say, look, if we want to confirm what this file is, we say readelf, something like that. But readelf is not available because we're running inside this Nix environment. So all the tools are prefixed with x86 unknown something, right? And so, but there will be a readelf there, and it's like a regular, because I'm running on Mac OS, but I wanted to use the x86 tools, right? Because we generated this hello world is an x86 ELF binary, right? So if I do build, sorry, hello OS, whatever it will tell me, it will ask me, okay, what do you want to know? I say -a, for example, let's show everything, and I pipe it to less. So now we know that ELF header is, it's an ELF file. It's x86 64-bit executable. This is different from x86, which was using 32-bit executables, but everything else is the same, right? So you can check that the entry point address is this number, and just for the sanity, you can probably search for this number here. Oh, sorry, like not this. Can we just copy it? No. I want to search for this. Maybe like this. And yeah, so what do we have here? That's a start symbol, right? And you may ask the question, okay, what is this start? Where is it coming from? But if you look at the source code one more time, and the homework will force you to do it, you will see that in this boot.asm, we advertise a global start symbol. And it's essentially this label, which is still 32-bit code. As I said, like, we'll come back in a second to this thing, but since grub leaves us in a 32-bit executable mode, I think there is a way to use a 64-bit version of grub, and then you will find yourself in a 64-bit mode. It's okay. We're gonna just switch into 64-bit mode ourselves in a second. I'll show how to do it. But essentially, originally you run a little bit of a 32-bit code, and then you switch into the 64-bit code, and that's where the assembler generates 64-bit instructions. Okay, so this is what we know now. So this gets us to again, we got the name of the file. What is it called? LOS. So we get this. And this thing is an L binary. I wasn't sure somehow yesterday because I wasn't sure what files grub loads, and maybe it can load multiple files, but we give it an ELF, and it has a start entry point, right? So makes sense. So kind of like we solved those problems which we wanted. Now we can concentrate on essentially working on this on the kernel which sits inside this ELF file. Almost all the booting is handled, and in a second I will we will talk about what is missing. Any questions? What I wanted to say that there are multiple ways to achieve a similar goal. So Philip says, I will be using a cargo-driven build, and that's his choice, and that's probably what a Rust person would do. It typically requires writing larger build scripts in Rust. I don't have a strong opinion what is better. Just for whatever reason, just wanted to illustrate that you can make files and cargo. One practical, pragmatic reason to kind of know that this way exists is if you at some point start working on the device drivers in the Rust on the Rust device drivers in the Linux kernel, because Linux now supports something what is called Rust for Linux. So it's kind of a framework which allows you build device drivers in Rust. Then you will see that since Linux kernel is a makefile driven build system, they have a custom custom build system. It's quite elaborate, but they said, okay, we're not gonna they kind of inverted it. And then in order for things to run, they essentially rely a lot upon makefiles. And that's just a very tiny example for how cargo and makefiles can be combined as well. A couple of other things which I wanted to show. So things like readelf are available, right? So that's what other tools as well. And in this Nix shell, you can add additional tools if you need. So you have traditional objdump, which is that's convenient, right? Just because Nix allows you to essentially pretend like I'm running an x86. All the issues with cross compiling is taken care of by running inside the Nix shell, right? What I want to show you, again, we can show, I don't know what's the good way. Objdump. Just looking for some kind of a flag, which is the most X. Okay, X is a good flag. It means all. So that kind of shows you similar to how we were looking at objdump or for the x86 kernel. It's a slightly larger thing because we depend on a bunch of different crates and parts of the core library, right? So it's not as easy, but essentially everything else is almost the same. Like what I wanted to show you. I don't know what's important. Something like that. If you want to confirm that you have remember we said I said two things are important in the linker script. I was wrong, so actually three. So another thing is the error at which to link the kernel. And we chose 1 megabyte, right? So essentially, if we take a look here, let me go back here again for a second. We said, look, guys, we start linking, and by virtue, grub will also load the kernel at this megabyte mark. This is exactly what x86 was doing, right? Because x86 said, okay, above the first megabyte, below the first megabyte, sorry, the memory is taken by various memory mapped IO primitives. Essentially, you can write in memory and it gets reaches devices, but essentially at 1 megabyte and above, it's available. We will take a look later that memory can have gaps, but typically a reasonably large chunk of the memory above 1 megabyte is available. So you of course, you're taking a risk. Maybe it's not available, but then, you're not going to boot, everything will crash. But on most x86 systems, it is available. But that's also important. And what I wanted to show you here, that, you see that header start and header end are the two symbols which we added to make sure that we see where the multi-boot header is. And so these two, header start and header end, and they are exactly at the very beginning of the first megabyte. So this is the first megabyte address, and how many bytes? 18 in hex, right? So, and then a bunch of different symbols. And if you say, look, but where is my wonderful kid? Where is my wonderful what did I do? What? Why is that? Build. If you look for the start symbol again, so that's just somewhere randomly linked at whatever address, right? If you look for your Rust main symbol, it will be there too. Where is it? Really? It's there, Like, that's linked to some other address, but everything, again, Rust behaves as a normal, like, game. There's very minimal runtime, similar to how you do it in C. You set up the stack so it can run. We can also do something like a disassembly to essentially disassemble the Rust code. And if you go to something like Rust main, not surprisingly, you will see there's some stack alignment, but this is the call to this core formatting function, which we're using for printing, right? And after that, we will have something like essentially an infinite loop, which we implemented there, right? So this jumps to itself, and there is no condition, so it will be jumping there forever, right? So what I'm trying to show here is that in contrast to other high-level languages like Java or C#, Java uses an intermediate representation before it compiles to x86, right? So Rust, during compilation, Rust also uses intermediate representation, but essentially the result is a human readable assembly. In most cases, you can actually understand what Rust is doing. What is, like, when you look at the assembly, you can understand what it's doing. Let me stop here for a second. Any questions? Okay, so this is good, and we got this. And finally, what I wanted to show you, let me exit here for a second. Where am I? What I wanted to show is that we added the debug target. The reason for that is, like, obviously, I say, okay, you guys wanna work on it. Like, I will assign a homework. You have to build something similar, but in general, like, as we go forward, and this is what I've seen in undergraduate class or the like introductory operating system class is that people, they kind of try to brute force the solution, right? So, you know, if it crashes, they just like randomly mutate the arguments or the lines of code, hoping that, okay, eventually it will boot, right? Our goal here is to avoid doing this as much as possible, and instead rely on stock tools like GDB to understand what is actually going wrong, right? And then we will add additional debugging primitives. We will actually add unwind to essentially, when there is a crash in a kernel, we will learn how to print the trace dump to see which calls were resulting in a crash, right? So right now we say there is no unwinding, board is panic, and that's fine. But when we will get an exception, we will implement our own unwind to make sure that we can at least say we know where we crashed. But what I wanted to show you here is that similar to how we do it in x86. So we have these two targets. One is run no X version, but under GDB, which means that we say, please, just instead of start spinning the QEMU emulator, just wait for the debugger to attach. And then if you have another target, if you do a GDB, then it will just essentially attach a GDB. So let me show you how it works. So if you do make run no X GDB, it will like start waiting for the GDB. Here we simplify a little, sorry, we use a Unix socket versus just a port. So it, like, you know, if you're running it and there is someone else using the same machine or you forgot to close it, you can open it multiple times, no problem. Make GDB, so that starts. Okay, I don't know if you can see it. So we say breakpoint on start. It happily does it. I say continue, start running. It says, okay, that's your first line of the start. Let's confirm in our code. We're using boot asm. Okay, start really does this, right? Okay, sure. So that's nice, but not entirely convincing. So we'll try to do something like, again, and it's very similar to, like, again, Rust works, everything works. It's similar to, let me just do another breakpoint on Rust main to make sure that we get there, right? Somehow gets the file wrong. We'll see in a second. But the point is that layout asm will give you this, right? So you say, look, this is what you are executing. Say next function, like that's essentially what runs inside boot asm.s, right? If I do something like layout split, then right now it will show me the source code of the assembly file, which is convenient. So I start running, go through all these functions, right? And it's totally fine if you want to integrate it with your Visual Studio, like we did in the undergraduate OS class. But I mean, in many cases, it's not necessary, but whatever works for you. So like, this is just single steps, everything is normal. If I press continue, I find myself inside this print formatting macro. That's how, like, I can probably, like when I said breakpoint on Rust main, so it's essentially just set a breakpoint here. But if I start running here, I will end up in this infinite loop and it will show you the source code conveniently, right? So I'll just do this right for now. And essentially try, like, the infrastructure is there. So when you start working on your homework, try to debug as much as possible. Obviously, like if you make a mistake in a page table code or something like that, then you get an exception, and then, you know, yeah, GDB will not going to help you because it will redirect you to some kind of weird, unless like to some kind of a exception handler, which grubs set up for us or something along those lines. So, but that's only until you guys understand how to write your own exception handlers. And essentially, here, let me just quickly before I quit this thing, so any questions about this debug infrastructure which we have? I will ask a different question. Do you guys understand how it runs? How do I even start what happens when I do make run nox? Let me write the command here. What happens? Who can tell me?
It compiles down the Rust binary or the Rust file into a binary and then links it to the multi-boot header, one thing, and then it runs that.
But how does it run it? I'm on Mac.
Well, I think it runs QEMU right after that.
Correct.
On that.
It runs QEMU, right? And how do we attach GDB to QEMU?
You start up GDB, and I think there's a command to. Okay. I actually don't know this part.
Yeah, no, and I mean, I also know only, and that's what I wanted to explain. But and if I ask you a different question, so what is QEMU?
It emulates the hardware that you specified, and then runs the operating system on top of that, I think.
That's correct. In a way, again, the devil is in the details. Your description is absolutely correct. So QEMU essentially, and I do discuss it in my undergraduate class, but essentially it starts as a process, right? It starts as a process in my macOS system, right? So it's just a process. I'm running on Mac, and I'm running on ARM, and QEMU itself, man, that's not a good sign. No battery. Maybe, hopefully, will last a little, but maybe I'll have to grab a cable, but we'll see. So essentially, it's written by a person, Fabrice Bellard, I believe his name is. It starts like kind of like a regular main. Years ago, the very first versions were easy to read, but like you can read the source code and understand what's going on, and it's something, it matches what you would wrote yourself. So it's kind of like, say, look, I implement a CPU emulator, meaning that QEMU takes our binary, our wonderful kernel, which we compiled with all the multi-boot header and everything like this boot hello, or whatever it's called. No, it's called hello OS. And it says, okay, look, like depends on how you set it up, but original versions were just starting on the entry point. And internally, QEMU implements, kind of roughly speaking, a CPU fetch decode execute loop. But essentially, it says, okay, if there is an entry point in this file, I will fetch the very first instruction from the entry point. I implement all the logic of this specific architecture, which I'm emulating, and I will maintain like a set of virtual registers. And like I assume some initial values, but if this, whatever, if this one adds 1 to register EIX, I will just add 1 to my initial value, right? And so it starts running by essentially fetching instructions and emulating all the effects of those instructions in this virtual register file, right? And well, sure, like it's not very hard. It's just like if one would teach an architecture class, that would be an excellent homework assignment. Of course, you need on x86. The details are awful because x86 assembly is a complicated beast. So essentially, disassembling every instruction correctly is a challenge on its own. QEMU, not surprisingly, will have bugs, right? So it's essentially says, okay, look, I do my best, but sometimes I screw it up. And that's fine, but you say, look, what about I/O? And original QEMU just emulated user level. And if this has some kind of a system call invocation, and let's assume we're using int instruction to invoke a syscall, original QMU was saying, well, I'll just exit and try to emulate the system call by using existing system calls in the operating system, right? Later versions of QMU said, okay, look, we're not going to be just emulating the user level of this architecture and some system call interface, like whatever, Linux or Windows or something. We're going to be emulating the entire machine. To emulate the entire machine, instead of like there is no system calls, right? Int, if you invoke int syscall, essentially what QMU will do, it will, who will tell me what it will do? If QMU emulates the entire machine and it sees the int, I don't know, OX40 instruction, which was a system call 60, it's like, I think it's 64 on in DAC. So it's a syscall on x86. What will QMU do for this? Anyone? What would be your guess?
So this is a system call, right? So
Mhm.
I would assume that QMU will take control of the process and do its task, right?
Wow, but and this is what I wanted to understand, so you to understand. So I started by saying that original versions of QMU were just emulating user processes. So essentially architecture, like for example, if I'm running on ARM, it can emulate x86 and it can run maybe a Linux binary. And when it sees a syscall, it will exit and into some kind of compatibility layer inside QMU, and eventually will try to invoke a system call on my Mac OS. If it's a file write, it will like write into a file. No, like if it's a file open, it will open a file. If there will be a write later, it will write into a file, right? But if we emulating the entire machine, there is like essentially what we're emulating is Intel manual, right? So you say I should faithfully, when I'm emulating the architecture, I should be faithfully following what the machine would do on boot, right? And well, that gets a little tricky. So on boot, for example, the machine should start loading the BIOS from whatever, the read-only memory on the motherboard, right? So essentially you say, look, I will follow this protocol. I will take the BIOS binary, it's called BIOS firmware, load it in memory and start running the BIOS, right? And we just only hope that the BIOS does something meaningful. And then the BIOS eventually, remember, kind of like, I'm assuming here a classical boot protocol, BIOS will fetch the master boot record from disk MBR and whatever, and we'll jump to the beginning of this boot record, and it will fetch it into this X7C00, as we remember from the undergraduate operating system class, right? And hopefully the MBR will then fetch the operating system, which in our case was x86, and then x86 will bootstrap itself and will start the first process, right? And by then, we assume that everything is configured correctly. Like if we continue this chain, so MBR loads x86 kernel, and x86 kernel creates like a page table and the first address space, and it has a very first process, let's say whatever, it's init or something, right? Or init shell, and init says I'm gonna exec into there was some init shell which execs into the real init binary, right? And this, in order to invoke this exec, there will be this int OX40 instruction, and the EAX will contain a specific number, right? Because this is how the system calls were implemented in x86. So int x40, just an instruction, EAX equals to some number which invokes a specific exec system call, is passed by the init shell program, right? So at this point, if we come back to this question, what do you think happens? again, now you know that the machine was essentially starting from nothing. It started from BIOS. Ideally, it should probably emulate maybe running what is called microcode updates, but probably it doesn't, but because no one knows what they do. But again, if I come back to this question about the int instruction, what do you think is happening?
Well, I know that some emulation software literally emulates like at the circuit level.
Mhm.
So I'm assuming that it goes pretty low level to simulate what some of these syscalls are doing on the actual like architecture,
Yeah,
maybe.
you kind of close. Yeah. So, but what is it doing? So, I clearly see that you didn't take the operating system class from me, but everyone else who did.
Well, like for example, would it be simulating like an adder for is it that low level?
No, it will
Okay.
not, because it's not needed, right? So, the other like things like gem5, which try to simulate architectural delays and stuff, might go. I don't think gem5 actually simulates adder, but some simulators do. But we don't need to, because our goal is to emulate x86. So we just need to emulate an effect of int instruction in x86. And what is the effect of this int instruction?
I'm guessing, okay, I'll just guess that it probably stops your execution and it goes back into main and calls the correct function that it has to simulate this syscall specifically.
Not exactly, right? Because it's a bare machine. So an int instruction is quite well defined on x86, right? I mean, like you can just int instruction, and like if you go here, you see it will, like, there will be a pseudocode of what the int instruction is supposed to do. Wow, it's complicated, right? But at some point you sell, well, who, like, this is exactly what QEMU will be doing. It will be following this pseudocode, but essentially it will do all these checks, and if it will try to read the interrupt descriptor table and essentially jump to the handler. It will save those 5 registers, switch to the kernel stack, but it will do exactly what a faithful x86 machine would do, like a real silicon. So it will, at a high level, it will like follow the interrupt descriptor table. And if it's interrupt 40, then it will go to the entry number x40. Whatever the handler is, it points to some memory, and it will essentially like faithfully follow interrupt protocol, and will switch and will start executing the next instruction as like from the beginning of this interrupt handler, right? And if since it was booting from BIOS, the assumption is that this x86 kernel did set up this interrupt descriptor table correctly, and this handler is actually installed. And the way everything works is that QEMU just says, look, guys, this will be, I will allocate some memory. Imagine you said you requested emulation of 256 megabytes of DRAM. I will allocate 256. It's virtual memory for me, but I will treat it as physical memory for you. And when you say that you want to access this interrupt descriptor table, when you were configuring it, you gave me an address, and this is where this interrupt descriptor table sits, right? And essentially, it will just simply read from this address whatever is there. It's pretty dumb. It doesn't keep track of what you wrote there before. It just trusts that your code will do something meaningful. If the entry in the interrupt descriptor table doesn't exist or invalid or does something funky, it will follow the fault protocols. Essentially, it will raise a, like, maybe it's a protection violation exception, maybe it's something else. It will again tries to like faithfully emulate this condition according to how x86 specifies it, but then essentially maybe it will just comes back to the same interrupt descriptor table to switch to a general protection fault handler or something along those lines, right? Make sense?
Actually, I did have a question.
Go for it.
I thought the operating system set up the interrupt descriptor table. Am I wrong
Correct.
about that?
You're
So
correct.
how does that happen here in this case? Like, let's say we ran the current version of your OS, which just says hello world. And
Yeah.
instead of being hello world, we called a simple, like the int syscall, for example. Have we even set up the table at this point, or?
No, no. Most likely no, unless the BIOS which you ran before, and QEMU does execute BIOS. If it's a UEFI BIOS, then it will execute UEFI BIOS. And then depending on whether the BIOS set it up or not, then you're lucky or unlucky. But in our case, like I was using x86 as an example here, which I was assuming that most people in this class kind of familiar with, and I wanted to.
Oh, okay.
But if we replace this x86 with our hello OS, then of course QEMU did run BIOS. We didn't use MBR, and instead of this protocol, actually we did use MBR, but we didn't like wrote it ourselves. We used grub bootloader to essentially just play with MBR and everything. And we booted this MBR was on this emulated optical disk. That's how we start the QEMU. Sorry, that's my optical disk attempt. It looks ugly, so I'll just better erase it. This is better, maybe. Oh, not better. But essentially, since as of now, we didn't talk about how to set up the interrupt descriptor table. So nothing is set up. If you do something funky, either this interrupt descriptor table, we keep track of all the registers of emulated architecture. So it's not just general registers. There will be interrupt descriptor table register. Maybe just point to some garbage. Maybe it points to nowhere. Maybe it points outside of the region of this memory. Or maybe it's actually points to the interrupt descriptor table, which was used by the BIOS or by the grub bootloader, because maybe it was processing interrupts. And then whatever, we will see that control goes there, right? But the moment we set up our own interrupt descriptor table, we'll get it back because we will know we will control where interrupt descriptor register on this emulated architecture points to, right? And in case of x86, if you remember how it was booting and everything, then everything, you started from an empty world. You trust the BIOS to do correct thing. It does correct thing. It passes control to a master boot record or grub in our case. That thing does correct thing. Grub, for example, in our case, fetches us the hello world, hello OS binary in memory and places it in this memory at the address 1 megabyte, right? So we're sitting here. Our start label is somewhere here. Sorry, again, handwriting is broken. And the Rust main is there. So QEMU eventually gets to, it will go through BIOS and everything, but eventually we'll get to the Rust and everything, right? But it just runs this fetch, decode, execute loop, instruction by instruction, emulating the effects of those instructions like a real machine would do, right? Make sense? Any other questions? It's kind of important to understand it. And I understand that it's unless you read about it or you dealt with it in the past, it's a little unusual. It's nice to, and I don't think I go into the details in the undergraduate class. And I don't go into the details here either, but at least I wanted to make sure that we understand that this is how it works. So we clear, this is we understand what happens when a specific instruction executes, right? Okay, and now back to this original question of, as I said, this is QEMU. It's a process. So my make file starts one process, and my make file also starts another process, which is called whatever, GDB, right?
Actually, I have a question about the makefile.
Yeah, go for it.
So I have the Rust branch checked out on the Mars research, the Hello OS.
Mm-hmm.
And I don't see the like run Nox GDB thing. Like it's not in my make file. I don't know.
Oh, yeah,
So
yeah,
how?
pool. Sorry, I apologize. Pool. We just edited it yesterday or maybe today.
Oh, okay. I see. All right. Thank you.
Yeah, no, like we're very last minute. I asked Zafang to help me with this, and he did it. Yeah, so if you pull, you will have it. And okay, back to GDB. Any other questions? Okay, so and these are two different processes. Yeah, go ahead.
Sorry. So how does GDB attach to QEMU?
Yeah, that's what I'm trying to explain.
Oh,
So
okay.
in here I might be a little wrong, but I'm pretty sure I'm okay-ish. So like it uses essentially a socket, which allows these two things to communicate, right? And there is a standard which GDB asks this QEMU to implement when GDB says like sends a command, something like a break at start. Internally, GDB reads all the debug information of this file. And I think at this point, it's just like a low command is just to say some kind of a breakpoint on a specific address. And there are different ways to implement breakpoints, right? So, and of course, like on a real hardware, when GDB connects to a real process, like if this is a GDB and I've started my foobar application, like and GDB connects over slightly different, but it will not connect over a socket, but we'll probably use a different interface. But when I say break, one way to implement a breakpoint is to take original instruction. Imagine it was move, and maybe move was taking multiple bytes because maybe it was a 4-byte instruction, right? And a way to implement a simplest breakpoint is to put XCC instruction, which is, I think it's an opcode for int either 3 or something. It's int debug essentially that passes control to the debugger, right? And so this way, this program can run almost forever, but eventually it just hits this instruction. It exits into the operating system. Operating system sees that the debugger is attached and it passes control to the GDB, right? And GDB has some way of introspecting memory and stuff. And what it will do is it has to actually, when you say step, it will replay this instruction. So it will either like temporarily restore the original opcode and then single step. And there is a hardware mechanism which allows you to say like, interrupt me again after this one instruction. So this instruction faithfully updates the registers of this process and stuff like that, right? And in case of QEMU, this interface is similar, but slightly different. So QEMU implements, because QEMU internally implements the whole machine. And so it does know how to implement a breakpoint, right? But GDB says, okay, I don't really know what you're doing. I'm just asking you to, if you have a ability to implement a breakpoint, please do. And then like come back to me later when you think like breakpoint it was hit, right? And I assume that QEMU just has some kind of a table and it says, okay, every time I fetch an instruction, I check whether this instruction whether this address has an associated breakpoint with it. And that's kind of like a high level story. And there might be more details to it because QEMU also has different modes of execution, and sometimes it actually drops into real, like it executes on real hardware or uses KVM virtual machine to run, and then it uses a similar trick like XCC to interrupt that virtual machine, or it can also try to use hardware breakpoints to interrupt the machine. But at high level, QEMU provides a certain interface, high-level interface, and GDB just sends those commands. And this interface allows you to read memory, write memory, stuff like that, right? And that's how everything kind of stitches together. So to some degree, like this is the explanation, but I should probably like look at more low level details if we really want to know them. But at a high level, this is how it works, right? That makes sense. Okay.
Oops, sorry.
Yeah,
How
go
does
ahead.
QEMU know how to like relieve control back to GDB?
It just like essentially stops fetching instructions and just like starts using this socket to send commands back and forth between GDB until GDB says continue, and then it starts running again. If it says single step, then it like emulates one instruction along those lines.
Yeah, okay.
And GDB is smart enough to understand that the binary was compiled from Rust. It can access like symbol information, stuff like that. That's why you can list variable names and stuff like that. But internally, GDB says when you say list like or print me a variable, like I think the low level interface to QEMU just reads the raw value from virtual memory potentially, right? And QEMU will translate implementing this command will translate from virtual to physical and then read the physical location and says, okay, this is what I see. I don't know what it is, but I don't care. But GDB makes sense of it for you, right? Okay, but okay, so we got the point. So we have this debug infrastructure. We can run. We see the like Rust and everything. That's what I encourage you to do. Control AX. No, that's GDB. I have to do. I have to say Control C probably if I can. I cannot anymore. Why? Control C doesn't work, so we will do Control X here. Just kill this one, your exit, right? But anyway, so that's the idea, right? So use this for as much as you can. Try to debug as much as you can. Don't guess. In this class, when you were doing the undergraduate class, it was okay guessing because there is a ton to cover here. You really need to precisely understand what's going on in your code and how the machine interacts with your operating system and stuff like that. And I want to come back to the main subject of the lecture. So, okay, we got this. We understood how it works. We understood the build system. We understand how debug works with QEMU. Our outline for the next couple of lectures is the following. So today, I wanted you to explain. I kind of told you that by the time we get to Rust main, we kind of said, okay, but we are kind of done, not? There is a tiny trick here. Grub leaves you in 32-bit mode. Rust main is 64-bit mode. And we need to kind of like switch from 32-bit mode to 64-bit mode. But unfortunately, on Intel, it's impossible to just do a long jump like we did for switching from real mode to 32-bit mode of execution. In order to enable 64-bit long mode of execution, you actually need to set up the page table. And we want to take a look at how to set up the very simplest page table today. Just this page table, it will be very, very minimal. It will use huge pages and will map memory one-to-one. And that is only needed so we can get to this 64-bit Rust code. We'll set up the page table in assembly. In theory, we could use 32-bit Rust. I didn't want to bother, although it's possible. You can probably do it in Rust. Maybe it would be more elegant. But after that, after this lecture today, I hope I will be able to finish. Instead of continuing with paging, we'll deviate a little bit, and we will first cover exceptions and exception handling. And then we will go to a simple physical memory, or we can call it a frame allocator. This allocator will allow us to allocate pages or physical memory for pages. Oh, sorry. physical memory of size 4 kilobytes, so we can construct a page table, because this very simple page table will be using just static memory, right? But if we want to build real page tables, then we need to allocate memory for these intermediate levels, right? And for that, we need this frame allocator, right? Or memory allocator. And after that, we will go again and construct a real page table, and some real address spaces. Sorry, spaces, right? So you got the point, right? So it's like there is a slight deviation here. So we start today on page tables, and I will teach a little bit on it. Then we switch back to exceptions. Then frame allocator needed to construct the real page table, and then we'll come back and construct the real page table, right? Make sense? So, okay, let's go back to this idea of getting to the long mode, right? So I have some slides here. So as I was saying, I'm not gonna switch. Okay, we can't switch to percent. How? So what I wanted to show you is the fact that on x86 it's just impossible to switch from the like into 64-bit mode of execution. So you cannot just say long jump into 64-bit mode. At a high level, you need at least some page table. And we'll discuss today in a second, like what page tables are possible. Again, since we're not going to use this page table for too much, we will just construct the simplest possible page table. But the absolute minimum instruction sequences which you have to do is that you essentially say, I created some page table. I will load the address of this page table into the control register 3. Before that, you need to enable this special physical address extension mode of execution, PAE, whatever Intel wants it. I roughly know the details, but I never followed why it's needed to just, I always do it mechanically. You can read more about it. This page table will be a very simple one-to-one mapping because, again, remember in x86, we wanted to remap the kernel at the second gigabyte. We're not going to do it here. It's not necessary. We'll stay kernel. The kernel will keep running at the first megabyte. It's linked to run at the first megabyte. There is no real reason to move it anywhere. Our process user address space will just start from different address. We can pick, for example, 4 gigabytes or something. Doesn't matter. And then just a couple of like technical details, like set long mode extension in a specific MSR register. MSR stands for what? Message specific registers. Okay, just Intel gives you an interface to talk to it, so that's the interface. Then we just simply enable paging, and only after that we can do a long jump into 64-bit mode. So let's take a look first. Let's take a look at the simplest page table we can create. If I ask you a question, how would you go about it? What is the simplest page table you can get running to just like to get the Rust main as fast as possible? Any ideas? Let's quickly review the x86 paging in 64-bit mode. In general, Intel supports a ton of different like paging variations, but the two main ones which you have to remember is that it supports either 4-level or 5-level page tables. So again, it's very, very similar to what we've seen before. Let me just quickly make sure that I can here. So this is a diagram from the Intel developer manual. Again, just a tiny move to the side. So imagine you want to understand how paging works on x86. And it's totally fine to ask ChatGPT, but at some point you say Intel developer. And it links you to this wonderful Intel page. Intel publishes the CPU manual about its CPU, right? And it has multiple volumes and chapters. Like it starts with basic architecture, then volume 2 describes the instruction set. So essentially every instruction and what the instruction is supposed to do will be described here. But then this volume 3 is a system programming guide. And this is what we need. So essentially, if I click on this one, it opens up, and then we go to the chapter, which is paging. And this is where those pictures are coming from. So, I mean, since I read this multiple times, it's hard to read. I agree with this. But since I read it multiple times, for me, it's more of a refresher. I quickly skip like all this 32-bit paging mode, PAE paging, and just immediately go to the 4-level paging and 5-level paging. And this is where this figure, which I have on my slides, is coming from. And if you ever want to come back and say, look, what's going on? Can we quickly read on how it actually works? You can just open this Intel manual and read more details, right? So back to the slide deck. So the slide deck is, it's very similar to how we were using paging in 32-bit mode. The page table contains 4 levels. So they give them names, PLM, 4, P, whatever, PD, PTE, page directory pointer table. Like we've only seen page directory and page tables. So this were like, I don't know how to properly count them. Level 1, level 2, they added 2 more in 4 levels, so level 3 and level 4, right? Idea is the same, but slightly different. So each individual level of a page table is still 4 kilobytes, right? Like it was before, so it's 4096 bytes. However, since now each of them will contain a pointer to the next level, right? And this pointer, it used to be 20 bytes because remember, it was 32-bit architecture. But if you align each of these 4 kilobyte pages at 4 kilobyte page boundary, the lowest 12 bits are always zeros, right? So you only need 20 bits to address the next level, right? In this example, instead of 20, you need 40, right? Which means that you have to fit, instead of like 32, this entry, each entry, like in this table, will be 64 bits, right? And which means that instead of, in the past, we were saying 496 divided by 32 was giving us 1024 entries. In this, on 64-bit machines, we divide by 64, and we will have 512 entries, right? So half the entries. And that's why instead of 10, we now use 9 bits to kind of like to locate the entry, right? Because each of these arrays is only 512. 512 bytes. Let me switch to chart. Pop up. Okay. Yeah, someone found. Okay, makes sense, right? Let me just quickly yell at my kids. I apologize. Okay, they're quiet now. What I was trying to say. Yeah, makes sense. So each of these is an array of 512 entries, right? And everything else is kind of like similar to as we've seen before. Let me just quickly erase everything on this slide. Control register 3 uses 40 bits to locate the root of the page table. You take the top 9 bits of the address, and bits from 0 to 47 are used now. Essentially, this pointer, which is 9 bits, selects an entry from 0 to 511, right? You pick the entry. Internally, this one will contain, it's a 64-bit entry. It will have 40 bits. Those ones is a pointer to the next level, right? And the rest will be flags. And we'll take a look at the flags in a second, and so on. So you say, what's the next level? Again, you take the next 9 bits, you select an entry here. This contains a pointer to the next level. The next 9 bits here chooses the entry in this level of a page table. Again, has a pointer, like 40-bit pointer to the next level. This, you take the next 9 bits, choose an entry here. Finally, it has a pointer to your physical 4 kilobyte physical page. It's 496 bytes, exactly as before. So you need 12 bits to figure an offset within a page, right? Make sense? So the 2 major changes is that Now, instead of 1024 entries, it's 512 entries. That's why we use 9 bits here. And of course, since the address space, physical address space is much larger, those are the physical addresses. You use 40 bits to essentially find the locations of the next levels. Make sense? Any questions? We're good on paging. So, okay, what's important for our purposes? Remember, when we were doing x86 also boots on a very simple page table. Who can tell me which one? Does anyone remember? It would be nice to be in a class. More jokes. But tell me, no one remembers how x86, which boot time page table it was using? People, tell me. I know that you know it. No? Or yes? Come on, I cannot do like quizzes in this class. No, remember, it was using what? It was using super pages, 4 megabyte pages, and it was using just one page, it's essentially, it's a page table which consists of one page, which has 1024 entries, which points to 4 megabyte pages. That's how you cover the entire 4 gigabyte address space. Remember this idea of super pages or like large pages. So this is important here as well. So this is what we want to do here as well. Good. Okay, so let's take a look. So Intel does the same trick here on x86 or on 64-bit machine. Essentially, it says, okay, guys, if this PS bit, which is it's a page super bit, whatever, is set, then we skip a level. And essentially we say, look, by the way, now we don't have to use like 40 bits of addresses. We can use 31 because it's like a super page. And so it's assumed to be aligned, right? And of course, since on the previous slide, one level, it has 512 entries multiplied by 4096 bytes, it equals 2 megabytes. So essentially that was covering potentially a region of 2 megabytes. So the super page is at 2 megabyte size, right? And then offset will be 21-bit, right? Makes sense? Okay, cool. That's nice. We have on 32-bit machines, we have pages of 4 kilobytes and 4 megabytes. Here we have pages of 4 kilobytes, 2 megabytes, because you combine, you essentially say the level is just points to one location in physical memory, right? But the same trick they played here. So they say, look, guys, if this level has PS set to 1, then it means that we're pointing to a 1 gigabyte page, right? And so again, alignment plays the trick, and you have only 22 bits here, but the offset, of course, becomes 30 bits, right? They don't play this trick at this level yet. I don't know, maybe they will in the future, but that gives us the pages of the following sizes: 4 kilobyte, 2 megabyte, and 1 gigabyte, right? And just if you check the mass, like 512 by 512 by 512 by 4 kilobytes, that's how it adds up, right? So everything kind of works logically together. And we say, sure, well, if we want to boot, we will be using, obviously, this kind of super page format, right? So you say, look, because you don't have to create additional levels here. You just need 2 levels. You need a root of the page table and 1 leaf, right? And you say, look, and for example, I will just map a couple, maybe 1, maybe 2, maybe 3, like identical mapping of those pages, right? So that will be enough for us to boot, like even more than enough, because remember, our kernel binary is 2 megabyte. Imagine we want to play with some address space, can be reasonably, like even 1 gigabyte will be sufficient for us to start running, right? So even 1 entry will be fine, right? And so we say, look, we will, and again, our game is to make it as simple as possible, meaning that we will create a page table which will map physical and virtual memory identically, meaning that virtual addresses if this is virtual, will be mapped to physical addresses 1-to-1, meaning that we don't need any shifts like in x86, nothing, right? We just say, look, if you address this virtual address, you can go directly to the physical memory. And we can say, look, how about just mapping first 1 gigabyte? That's totally fine. Why not? Since we anyway have to create these 2 levels, so meaning that we at least need 2 4-kilobyte pages, we can probably connect them, like one pointer connects here, all the other entries are invalid here. But for this one, since we have 512 entries, we can probably utilize them all, because we're not going to lose anything. You can map entire 512 times, and it will be 512 gigabytes. But it's just a temporary page table before we really switch to something more fine grain. Or maybe we can run on it for a while and then create address spaces, fine grain address spaces for user processes, stuff like that, right? But that's essentially, like, if we construct this page table and we do this, whatever the minimal steps, we'll get into this 64-bit code, right? That's what I wanted to get to today, right? Make sense? Any questions?
Can you remind me why we needed this page table to get into 64-bit mode? Like, what was the process of going into 64-bit mode that required the page table?
Yeah, and to be honest, every time I read about it, I'm surprised myself, and I don't have a good answer for what was the reason. But essentially, Intel tells you that you cannot run in 64-bit mode without a page table. Okay. The reason is probably I'm speculating, so not 100% sure, and I wanted to come back to it. So remember, I kept saying that when Intel transitioned from 32-bit mode to 64-bit mode, it almost completely killed segmentation. The global descriptors table is still there. It's required. It has to be there to boot, but it essentially does not allow you to specify the base and a limit, which means that you cannot anymore like really control the size of the address space. You just always max, like base is 0, max limit, right? And that's probably, they say, if you really want to run in 64-bit mode and to make anything meaningful, you need a page table. Maybe I'm wrong. Maybe it's a wrong explanation, but that's another thing which happens, another difference between 32 and 64-bit mode. But I can investigate for you, to make sure that I know it for sure as well. But every time I look at the source code, I keep forgetting about it, and I say, look, why are we even like setting up a page table? Let's do it in Rust, because in Rust it would be more elegant. And I like comment out the assembly code, and then it stops booting, and then I remember again. Make sense? So essentially, Intel just made this decision. There might be a good reason for that.
Would it be possible to add another Rust target JSON that has a 32-bit architecture?
Correct.
And
that's
then set up the page table in there?
Yeah, correct. And that's one way to go about it. Totally possible. Yeah. I didn't want to deal with it. Like at this point, it's a matter of choice. I chose to do it in assembly. I think the code is so minimal, and I'll show you it in a second, that it's probably not worth dealing with another target, but maybe you can, yeah, and just be happy about it, yeah. And maybe, I don't know. And probably that's what Philip is doing in his bootloader crate. I didn't look, but maybe you looked and maybe you know how it works, right? I should take a look how he does it, but I stick to assembly. Why is that? Don't have a good answer, honestly. Like it's just a personal choice at this point. Anything else? And I'm running a little late. Okay, cool. And a 5-level page table, I just wanted to make sure that we all understand it. At some point, if the 4-level page table allows you to essentially go up to 256 terabytes of memory, at some point Intel became so powerful that they were producing those machines which had memories which were approaching this 256 terabytes. They said, okay, let's do another level. It's exactly the same, but now it can go, if you multiply 256 terabytes by 512. If you add another level, you get this number, 128 petabytes. And essentially it's everything like before, but instead of like CR3 pointing to PML4, now there is another level and it's PML5, right? But that's not super surprising, and sure, okay, that's what we expected. Okay, let's quickly switch. I wanted to show you the code which does it. The code in my Hello OS example, it's actually, I don't know where I got it from, but it's a little bit broken. So we are switching to a different operating system kernel, which I was also participating, and actually I was actually even writing it. And this one, it's called Redleaf, but I will move this code, or it will be part of your homework assignment to implement this code, right? But essentially, this does it more cleanly. So it's essentially exactly, it's a similar code, but essentially it starts at start label here. It does those checks similar to the checks which we did in the Hello OS. And then it goes to this function, which is set up huge page tables. And if we go here, what happens here is this. I say, look, I have these two variables essentially. P4 is for 1096 bytes, and P3, I just need 2 regions of 4 kilobytes, right? Because I will be only manipulating 2 leaves of the page table. What's critical here is that they have to be aligned at 4096 byte boundary, right? Because remember, like all this data structure, this 20 and 40, what is it, 20 and what was the number? I already forgot. But essentially assume the alignments. And in order to make sure that it's all initialized with zeros, I put it inside the BSS section, right? Also makes sense, right? But again, if you decided to code it in Rust, like Talia was suggesting, then it will be like whatever, const initialization in Rust, right? But essentially what my assembly code is doing is it just says, okay, I will in the very root of the page table, right? I will use entry number 0. And the only flags, sorry, I didn't talk about the flags, are present and writable. So I put this 1 here. And I specifically, like I first loaded the address of the P3 table, right? So since virtual addresses equal physical addresses, like the linker already produced the correct address, so I can just use this P3 table variable. And then I OR it with this additional bits, because I apologize for not talking about it in a lecture, but if you look at this like individual entries in this table and you say, look, what are those bits? So this is the bit 0, present might be 1 to reference the next level. And we're talking about 5 here. So in our case, it will be probably something different. And this read write. So I'm just setting these 2 bits, 0 and 1, right? And the top bits are actually, those are the bits which point to the physical address of the next level, right? And so I do that, and then I say, go to this label, map the memory into this next level. And what it does, it says, okay, I will be going in this 1 gigabyte increments, and essentially I just implement a loop here. I initialize the counter here, right? And I'm trying to check whether it's whatever reason, this code maps only 32 entries. This is fine, okay. So you can map in even 1 gigabyte will be enough, right? But essentially, that's fine. And what we do here is that this is where this ugliness coming in. So like we don't have 64-bit mode of execution yet. So you have to kind of access low bits and high bits separately. And it's a little ugly. And I agree, like, okay, maybe at this point, maybe switching to Rust will help you to prevent a silly mistake, right? But like, okay, I'm still in assembly here. And here, here we add 1 additional bit. So it's, remember this PS bit. It says that the next level is huge, which means that I don't have to go, the hardware will not go into any other levels. It will just stop there. And essentially, I'm just initializing the page tables, right? So just to illustrate the point, to make sure that we all understand what's going on here, is this. So what I'm doing is that I'm saying I have page table. What's the name of the variable? Before table. I only like put one element here, and it points to P3 table. And apparently here I'm like using 32-bit entries, and it maps memory from 0 to 1 GB multiplied by 32, right? Make sense? So that's all what happens, right? And then I will load this inside the CR3. And after that, everything else is reasonably mechanical. So essentially I say, look, guys, I'm returning from this function, coming back here from enable, I'm sorry, coming back from back to start, coming back here, line 16, then call enable paging. Maybe, okay, let's keep
What
scrolling.
is this CR3 register doing again?
A CR3 register contains the root of the page table on Intel architecture. Control register.
Okay, so the architecture refers to that register to deal with pages, basically.
Yeah, essentially when the hardware wants to figure out the root of the page table, it allows the operating system to control this register right into it. And so essentially it just follows this pointer and starts reading from the root of the page table.
Okay, thank you.
And so here this is more of a mechanical sequence. Like here, there are references to individual chapters of the Intel developer manual, which tell you why you need to do it. And it comes from Philip actually again. So essentially we say, well, that's the protocol which Intel wants you to play. It says in a control register 4, enable this physical address extension. Okay, you cannot update control registers directly. So you first save them into the general registers, EAX, set the bit, move it back into the EAX. It says load the root of the page table into the control register 3. This is what's happening here. Set the long mode in this MSR. It's again just an interface which Intel provides. It's a specific MSR number, this C00080. You do a read MSR, result in the EAX register. You set the bit and you write it back, right? And finally, you say, look, I will enable paging in the control register 0. You read CR0 again, set the bit, which enables the paging. You write it back. After that, you return. And when you return at this point, only now you're allowed to switch to a 64-bit mode of execution. And the way you do it, So no, you still need to load a global descriptor table. Just 2 more minutes. I apologize for being late. You load the global descriptor table. So let's take a look at how I initialize it. So again, I use assembly, which is not ideal and which is actually kind of a little bit confusing for me. But essentially, I'm setting up, like that's what I was asking ChatGPT. Like essentially, I asked, what is this? Which bits are this code setting? Like essentially, and ChatGPT tells me, okay, you're probably very clever or copied it from somewhere, which is true. But essentially, I'm setting the bits which are executable segment. It's not sure what this means, but P means present, which is valid, and this is a 64-bit segment. And essentially, I'm initializing this thing. This is essentially the GDT itself. This is entry 0 in GDT. It's required by Intel. This is my only code segment. And after the GDT, essentially, you need to create a special format which contains the address of GDT and the size, like essentially the size of the GDT and the address of the GDT. And then you use this pointer, GDT64 pointer, to load it into the global descriptor table. So essentially, there is an instruction. It's just the Intel gives you an instruction, and this instruction requires this data structure as an argument to this instruction. That's why it's created this way. And after that, I can jump to long mode. So essentially I say, look, now I jump to sorry, it's a piece of function which starts other CPUs. Let me just go back to this, to the start. So I jump to the start 64 label, which is here. And after that, my assembly in 64-bit mode, I initialize the segments to zeros. And after that, I can call Rust main. And remember that we set a stack at the very beginning. It's essentially right when we started here, right? So at this point, I will find myself in this Rust main function. Everything is running. I said that it's a little bit confusing for me because I thought that in order to get this thing running on x86, you need to declare both the code and a data segment. But the data segments are set to 0, which is probably fine because Bayesian limits are ignored, but I need to investigate a little bit. So that's the only thing which was a little confusing for me, right? But that's, other than that, we kind of like stitched everything together. So you start from like in 32-bit mode, set up a simple page table, and then enable segmentation. Segmentation is enabled, but you long jumped into the 64-bit mode, and then you can call Rust. And that kind of completes the boot sequence. At this point, we know everything what was happening from the beginning of when we started running, when we were loaded by grub, to when we were like inside our Rust main function. So let me stop here because I'm over time and I apologize for that. Any questions? Yes. Okay, let me upload the slides and videos right away. So I was just behind. And the homework. And the homework, I will try, like, at this point, I'm ready to assign the homework, essentially. So I think you have everything what you need for the homework. And the very first homework will be essentially to re-implement the same code. So I will give you the skeleton of the build infrastructure, pointers to the Hello OS, you know where it is, pointer to the red leaf, and you have to like kind of like stitch everything together. If you feel like changing the build to make sure to use 32-bit Rust instead of assembly, that's fine. Like I would be super happy to see how it works and everything. So go for it. But and we have the debug capability, so you can run GDB along with QEMU, so you will be able to debug. But it will be still confusing because until we set up the exception handlers, it might still throw you away. But at least you will see the instruction which throws an exception, which is also like a step forward. Okay, good for now.
Could you remind me how, like, once you start QEMU and like the debug mode and like attach GDB, how you actually like jump into the initial code? Because it's not as easy as just like running.
Yeah, no, I did this like right, and I started GDB. Then I just sorry if you don't see this, I don't know.
I see.
I just set a breakpoint. B is for breakpoint on start.
Yeah.
I mean, I
I
don't
see.
here in my undergraduate OS class. I can send a link which like talks about basics of GDB, but there are probably like a ton of resources online. I mean, in the end, it all boils down to GDB. In the undergrad class, we also have a setup which allows you to connect GDB to Visual Studio.
I just didn't know exactly where to set the breakpoint.
Yeah,
So-
no, but yeah, so you can set anywhere. I set on start. You can set like any symbol will work. Breakpoint, Rust main will work as well, right? You can set a breakpoint on address, stuff like that. Anything will work. And you're welcome to watch the recording as well. But yeah.
And can you set it like how early can you set it in the
Oh, nothing is
process?
running yet. So not even bias still running. So QEMU just waiting.
I see.
Yeah. So you essentially you can set it on any address in a system, but watch out. So like it's a little tricky because I think it will play the machine faithfully. So it will start in some 16-bit mode of execution. So
Right.
yeah.
Yeah.
Okay. Okay, good. Thank you, guys. So then Monday is a holiday. I will try to assign the homework today or tomorrow. I'm behind on my own deadline, but I'm like trying to catch up. And or at least maybe I will set up some bare bones thing and you can start working and I will add more instructions. So you can work through the long weekend. I think like week is enough. So roughly maybe like by next Wednesday can be due, maybe by next Friday, so we can keep rolling. It's a very simple homework, right? And so because the next ones will be more advanced, so we have to get going. Okay, this is probably it. Thank you so much.